Hello friends, myself Dr. Nandakumar Raubale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 2. This is our 16th lecture. In previous lecture, we have discussed about a numerical on psychometric properties and use of psychometric chart. So today we are going to discuss about the psychometric processes such as sensible heating, latent heating, humidification, dehumidification, and so on. Then for today we are going to discuss sensible heating and sensible cooling, whereas we'll be discussing about bypass factor of heating and cooling coil, efficiency of heating and cooling coil, and a numerical. Now let us consider sensible heating. So what this sensible heating is, let us consider a electrical coil. So this is electrical coil, and this is the air which is entering at a temperature T D1. So T D1 be the temperature of air entering over the coil, which is heating coil. We call this as a heating coil. Heating coil. So over this heating coil, air having drivable temperature TD1 is passed, whereas the temperature of heating coil is TD3. Say TD3 is the temperature of heating coil, whereas the air which is passed over this heating coil comes out at a temperature of TD2. So here what we have to assume is, first, temperature of air TD1 at inlet is less than temperature of heating coil TD3, and when this air passes through the heating coil, then its temperature increases to TD2. So this TD2 is also less than the temperature of heating coil TD3. So TD3 is highest temperature in this case. So when air is passed over this heating coil, then this air absorbs sensible heat and its temperature increases. So now this process can be shown on psychometric chart. Let us consider the air which is entering into this coil TD1, which is at temperature 20 degrees Celsius drivable temperature. Say this is the point where point 1. So at point 1, air enters into this coil, and because of heating, its temperature changes from 20 degrees Celsius to 30 degrees Celsius. So it comes out at temperature TD2. So initial temperature is TD1, and it comes out at temperature TD2. This is temperature TD2. Then the temperature of heating coil is TD3. Say it is 40 degrees Celsius. It is 40 degrees Celsius. So this drivable temperature is 40 degrees Celsius. This is TD3, and TD2 is 30 degrees Celsius, and TD1 is 20 degrees Celsius. So the air which is at 20 degrees Celsius passes over this heating coil, and it comes out at temperature TD2, which is the temperature of air, drivable temperature of air coming out of this heating coil. So now this process is represented by this horizontal line 1 to 2, starting from left to right. So this is called as sensible heating. So if we continue again, then here we will have point 3, that is temperature of TD3, temperature of heating coil. So now at first point, let us consider the humidity, which is known as specific humidity omega, omega 1, omega 2 and omega 3. In these three cases is going to remain same. Say approximately it is somewhere here 0.009, so it may be 0.009, say, that is kg per kg of dry air. So this is going to remain constant, whereas this relative humidity, so here relative humidity in first step at point 1 is say 50, sorry, it is 50%. Relative humidity at point 1 is phi 1 is 50, whereas the relative humidity at point 2 is approximately 30. That is nothing but relative humidity is phi 2, which is 30. That is nothing but 30%, say 30% and 50%. So in sensible heating, the relative humidity decreases, whereas drivable temperature is going to increase, but the specific humidity remains constant, whereas enthalpy is going to increase. So enthalpy H1, if corresponding to this, if we find enthalpy, it will be 40 at inlet, and enthalpy at outlet for the air maybe somewhere here it is 50 kilojoules per kg. So this is how the sensible heating process works out. Now let us consider, that is sensible heat. So let us say the air enters at TD1 and leaves at TD2, whereas temperature of coil is TD3. Now we can see here the amount of heat added is equal to H2 minus H1. So as we have shown here, point 1 and point 2, H2 minus H1 is the amount of sensible heat added. So now this heat which is added can also be given as that is H2 minus of H1, that can again be written as mcp delta t. So in that form we can write. So first of all, the amount of heat which is added is used to increase the temperature or enthalpy of air, and then some part of heat added to this air is used to increase the enthalpy of water present in the air. Therefore it can be written as, heat added can be written as CPA, specific heat of air, into TD2 minus TD1 TD1. So this is nothing but amount of heat used to increase temperature of dry air without water vapor, and then plus of some part of heat is used to increase the enthalpy of water vapor present. So omega be the specific humidity into CPS, specific heat of steam, water vapor, into TD2 minus TD1. So this again can be rewritten as CPA plus of omega CPS so this TD2 minus TD1 is taken as common. Therefore in the second bracket TD2 minus TD1. So this we can write as second equation, or this CPA plus of omega CPS can be written as CPM in bracket TD2 minus TD1. So where this is heat added Q, specific heat added Q, where CPM, is equal to CPA, specific heat of air, plus of specific humidity omega into CPS, specific heat of water, that is steam. So this is what is nothing but the specific or humid specific heat. CPM is known as humid specific heat. Humid specific heat, and this value of humid specific heat is generally equal to 1.022 kilojoules per kg Kelvin. Kilojoules per kg Kelvin. So this is how this sensible heat added is given by this. So one thing we can remember, so we have 3 points, point 1, 2, 3. So the temperature of air entering is TD1, and corresponding to this we will get enthalpy H1 from this scale. Then corresponding to point 2 we get enthalpy from this scale. This is H2, so this is H1, H2. So this process 1 to 2, from point 1 to point 2, is known as sensible heating. So here H3 is the enthalpy corresponding to TD3. So we can take H3 also. So now this was about sensible heating. Now we are going to think of sensible cooling. So first, this sensible heating can be given Q is equal to 1.022 TD2 minus TD1. So this is the sensible heat added in terms of kilojoules per kg. Kilojoules per kg. Now coming to sensible cooling. So here let us assume that the cooling process, so TD1, let TD1 be the temperature of air entering over the coil, whereas TD2 be the temperature of air coming out, whereas TD3 is the temperature of cooling coil. So in this case TD1 is greater than TD3 because it is cooling process. It is expected that temperature of air when passed over the cooling coil should reach to the cooling coil. Practically it does not reach to the lowest temperature TD3. So TD2, temperature of air coming out, is still greater than temperature of cooling coil TD3. let us consider the dryable temperature of air as say this is 38 degrees Celsius. So we mark the point at 38 degrees Celsius here. So first point we mark, that is TD1, temperature of air entering the coil. TD1 is at point 1, say. Then this coil, when this air is passed over the coil, so this temperature of air gets reduced to TD2. Say we assume that it reduces to 30 degrees Celsius. So TD2, temperature of air coming out of this coil is TD2, whereas the temperature of cooling coil is, say for example, 22 degrees Celsius. So 22 degrees Celsius is 0.3, 0.2. So temperature of cooling coil TD3 is the lowest temperature. So when the air is passed, hot air is passed over the coil, its temperature reduces from 1 to 2. So 1 at point 1 temperature is, say, TD1, temperature reduces to TD2, whereas the temperature of cooling coil is TD3. So this is called as a cooling process. So in this cooling process is similar to heating process, but it is exactly reverse. This moves from right to left. So here we can find the humidity, specific humidity, omega 1 is equal to omega 2. So specific humidity remains same, whereas relative humidity, if we see, so relative humidity initially is 30%. So phi 1, if we assume here it is 30%, and after cooling the relative humidity increases to, say, it is in between 40 and 50, means it is 45. So relative humidity phi 2 is 45%. So relative humidity increases from 30 to 45%. So this is going to happen in case of sensible cooling. So now let us consider, so this is TD1, temperature of cooling coil is TD3, and air coming out is TD2. So where what we assume is temperature TD1 is greater than TD2, sorry, less than TD2, and TD2 is less than TD3. So temperature of air is greater, whereas temperature of coil is the lowest, whereas the intermediate temperature TD2 is the temperature of air leaving. So now again we can show this process somewhere here, point 1 to point 2. So this process 1 to 2 can be shown, whereas corresponding to 2 you can get the enthalpy H2, and corresponding to point 1 we can get enthalpy H1, and if we move this point somewhere 3, the enthalpy 3 can be obtained here, X3. So now for this also the heat rejected can be given as H1 minus H2. H1 minus H2 is nothing but heat rejected in this process, H1 to H2. Initially enthalpy is higher and enthalpy after cooling is low, therefore H1 minus H2 is the enthalpy or heat rejected. So this can again be given as Cp A in bracket TD1 minus TD2 . So this is the amount of heat energy rejected to cool air from temperature TD1 to TD2. So this is the amount of enthalpy rejected by simply dry air, whereas the air contains water particles, that is humidity. So this specific humidity omega into CPS into TD1 minus TD2 is the amount of heat rejected by the water particles in suspension or humid air. So therefore this can be rewritten as TD1 minus TD2 is common in two terms. Therefore we can write this as CPA plus of omega CPS into TD1 minus TD2. So this is heat rejected Q, or this can be written as CPM TD1 minus TD2, where this is Q. So this CPM in general practice it is equal to 1.022 TD1 minus TD2. So this is heat rejected. So we can write here as where CPM is equal to CPA plus of omega CPS, and which is known as humid specific heat, which is known as humid specific heat. Humid specific heat, and value of which is 1.022 kilojoules per kg Kelvin. So now further, the sensible heat per minute added or removed can be given sensible heat sensible heat per minute can be given as, if we multiply this factor mCp delta T, so sensible heat per minute is given by a mass of air Ma into CPM, that is humid specific heat CPM, into delta T, where delta T is the difference in temperature, delta T. So delta T means TD1 minus TD2 or TD2 minus TD1. So this can be written as, again, Ma can be written as specific volume V into rho into CPM into delta T. So that is nothing but, here mass is equal to specific volume into density. So this is nothing but volume flow per unit time. So where small v is rate of airflow rate of flow of air here in meter cube per minute, and rho is density of moist air. It is density of moist air. Moist air, and that is generally 1.2 kg per meter cube of dry air at the standard NTP, that is 20 degrees Celsius dryable temperature and 50% relative humidity. So where CPM is nothing but humid specific heat, so density is taken as 1.2 kg per meter cube. And this CPM is specific or humid specific heat. Humid specific heat. In kilojoules per kg degree Kelvin. In kilojoules per kg Kelvin. So now this can be written as specific heat or sensible heat. Sensible heat per minute is given by this specific column we take as it is. Density is taken as 1.2 into 1.2 into CPM is 1.022 into delta T. Delta T means TD2 minus TD1, that is in kilojoules per minute. Or on simplification, if we divide it by 60, then it becomes in kilojoules per second or kilowatt. So dividing this by multiplying these two terms, 1.2 and 1.002, we get 1.2264 into V into delta T whole divided by 60 in kilojoules per second. Kilojoules per second. On simplification, this works out to be 0.02044 V into delta T kilojoules per second, or that is in kilowatt. Or kilowatt. So this is about sensible cooling. Now let us see what is bypass factor. Now this bypass factor is nothing but, say for example, this is a cooling coil or heating coil. So this may be cooling coil or heating coil. It can be a cooling coil or heating coil. So the air which is passed, say for example air inlet, this air which is passed over the coil, out of x kg of air, so only 1 kg of air. We are passing 1 kg of air. So out of that, only this portion of air is passing over the coil. That is x kg is passed over the coil, whereas 1 minus x kg is not passing over the coil, or that is not coming in contact with the coil. So that there may be the reason that the number of fins provided in unit length, that is pitch of cooling coils, may be less or less dense the coil, or number of rows in coil in the direction of flow. So if there are less number of coils, then the bypass air will be more, so air may not come in contact with the coil. Or the velocity of air is also one of the factor which affects on the bypass factor. So air is going to bypass in the sense the air which is not coming in contact with the cooling or heating coil. So for this, let us assume that 1 kg of air is passed in the system, whereas x kg is going to pass over the coil, and 1 minus x is not coming in contact with the coil. So therefore, balancing the enthalpies we get say here, x kg is going to pass over the coil. So x into cpm into td1. Temperature of air is td1, which is entering. So this x amount of air is passing over the coil, plus 1 minus x, sorry, uh, x is not passing, 1 minus x is passing over this. So here x is not passing without coming in contact with the air. So this x part of air is bypassing. X is bypassed, whereas 1 minus x comes in contact with the coil. Say 1 minus x comes in contact with the coil where the coil temperature is TD3. So therefore 1 minus x comes in contact with TD3. So 1 minus x cpm into TD3 is the amount of air which is coming in contact with the coil, and x kg is not coming in contact with the coil, that is bypass is x. So that is nothing but total amount of air which is passing over the coil is 1 kg, 1 into cpm, and coming out at the temperature of TD2. Air entering is having temperature TD1, air leaving is having temperature TD2, and TD3 is the coil temperature. So therefore, by simplification, this we get here cpm is on both sides, cpm gets cancelled, specific humid specific heat, cpm and cpm gets cancelled. So now on simplification, what we have here is x td1 plus of td3 minus x td3 is equal to td2. So TD3 is transferred on right hand side. So what is going to remain here? X TD1 minus X TD3, which is equal to TD2 minus TD3, whereas x is taken common here, x TD1 minus TD3, which is equal to TD2 minus TD3, or this x is equal to TD2 minus TD3 divided by TD1 minus TD3. So this x is known as a bypass factor of the coil. So this x is known as bypass factor of coil. So x is called bypass factor. Bypass factor of coil, generally written as BPF. It is written as BPF. So this is the bypass factor of heating coil. So we call this as, this is bypass factor of cooling coil or heating coil. Just a minute. TD3 minus TD3. Okay. So this is bypass factor of cooling coil. Cooling coil. So if this is a cooling coil, then we get this bypass factor, or x is equal to TD2 minus TD2 minus TD3 divided by this is for heating coil. So if this is written as TD2 minus TD3 whole divided by TD1 minus, this is TD3 minus TD2, TD3 minus TD2 divided by TD1 minus TD3. This is the bypass factor for cooling coil. Bypass factor BPF for cooling coil. So here what we can see is the difference of temperature of air coming at outlet and temperature of coil, maybe heating coil. So this difference is in numerator, whereas the temperature of heating or cooling coil minus of temperature of air at inlet is in the denominator. So this if we find, that is called as a bypass factor. So now let us consider the efficiency. So efficiency of heating coil is 1 minus bypass factor. So here 1 minus bypass factor of heating coil is given by TD3, 1 minus TD3 minus TD2 divided by TD3 minus TD1 minus TD1. On simplification, this efficiency of heating coil works out to be TD2 minus TD1 whole divided by TD3 minus TD1. So this is bypass factor of efficiency of heating coil. So efficiency of cooling coil is again 1 minus bypass factor of cooling coil. So this is again given by 1 minus TD2 minus TD3 whole divided by TD1 minus TD3. On simplification, the efficiency of heating coil, cooling coil, this is for cooling coil, is given by TD1 minus TD2 whole divided by TD1 minus of TD3. So this gives us the efficiency of cooling coil. Now let us consider one problem. So in this problem, so what is given that we see here first. So atmospheric air at a dryable temperature dBT is given as 15 degrees Celsius. So given dBT as 15 degrees Celsius, then wet bulb temperature 11 degrees Celsius. And the atmospheric pressure barometric reading PB is 760 mm of Hg. PB 760 mm of Hg. Now assuming bypass factor to be 0.5, he enters a heating coil whose temperature of heating coil TD3 is 41 degrees Celsius. So this dryable temperature is TD1. Dryable temperature of air is 15 degrees Celsius at inlet, whereas the heating coil temperature is 41 degrees Celsius. Then he says that the bypass factor is 0.5. The bypass factor is 0.5. Bypass factor is 0.5. Then he is asking us to determine dryable temperature, wet bulb temperature, and relative humidity of air leaving the coil. Determine the sensible heat added to the air per kg of dry air. So now what he is asking us to find is dBT, WBT, relative humidity. So he is asking us to find out dBT, WBT, relative humidity, DBT, WBT, relative humidity of air leaving the coil, determine sensible heat added, that is H2 minus H1. Is also asked. So now what is asked is dryable temperature of air leaving. So how to find out that dryable temperature? Bypass factor we know. Formula for bypass factor is given by TD3 minus TD2 divided by TD3 minus TD1. So now in this case we know TD3 is known, we know TD1, TD2 is not known, whereas bypass factor is also known. Only dryable temperature can be obtained. So once we know dryable temperature of air leaving this, then we can find out wet bulb temperature also. So we can find out wet bulb temperature and relative humidity from the psychrometric chart, whereas sensible heat can also be obtained from this what we call as a psychrometric chart. So now first of all we will discuss it with the help of psychrometric chart. Before that we must find out TD2. So bypass factor given is 0.5, which is equal to TD3, which is given as 41 degrees Celsius, minus TD2 we don't know. TD2 we want to find out dryable temperature of air leaving this heating coil. TD3 we know, that is 41 minus TD1 is 15 degrees Celsius. So from this we can get TD2 which is equal to 28 degrees Celsius. So we know TD2 as 28 degrees Celsius. So now let us plot this on psychrometric chart. So consider this temperature as 15 degrees Celsius. At 15 degrees Celsius and wet bulb temperature as 11 degrees Celsius. So from here 11 degrees Celsius somewhere here, 0.1 we can mark, whereas the dryable temperature of heating coil is 41 degrees Celsius. So in between these two, 41 degrees Celsius, somewhere this point is 3. And then after that we have seen this dryable temperature as 20 degrees Celsius. So 28 degrees Celsius, exactly above this here somewhere 28 degrees Celsius, 0.2. So 1 2 3. So now corresponding to these things on this psychrometric chart, you can get H1 H2 TW2 wet bulb temperature corresponding to this point 2. If we see, it is greater than 15, is greater than 15. So the wet bulb temperature of air can be more than 15, that is it may be 16 degrees Celsius. Approximately 16 degrees Celsius is the wet bulb temperature. So first we find out wet bulb temperature WBT from this psychrometric chart. WBT is equal to 16 degrees Celsius. So corresponding to point 2, wet bulb temperature of air leaving. So air was initially at point 1, it is sensibly heated and it comes out at point 2. So wet bulb temperature is 16 degrees Celsius, whereas the relative humidity, if we see, so here corresponding to this curve, relative humidity is 30 degrees Celsius. So phi 2 is 30 degrees Celsius, sorry 30%. So corresponding to point 2, if we see here along this curve, humidity is 30%, whereas enthalpy H2 and H1 if we see, Corresponding to point 1, if we take this enthalpy H1 is equal to 30 kilojoules per kg, whereas H2 is equal to 42 kilojoules per kg, we can find here. So amount of heat added can be H2 minus H1, that is 42 minus 30, that is 12 kilojoules per kg of air. So Q amount of heat added is 12 kilojoules per kg of air. So this was asked, I think. So here dryable temperature, wet bulb temperature, relative humidity H2 minus H1. So we have obtained dryable temperature dBT as in calculation itself we have obtained here 28 degrees Celsius. dBT is 28 degrees Celsius. Wet bulb temperature is 16 degrees Celsius. Then relative humidity is 30%, and H2 minus H1 is 12 kilojoules per kg. So these values will be different if you are using actual chart and pencil. Then we can find out more accurate values of H1, H2, everything, and then phi. So therefore you practically use this psychrometric chart and try to simplify. So today we stop here, and in next class we will be looking at the process of humidification and dehumidification. Thank you.